right, we've made it to the end of circular motion. The last thing I want to talk about is angular momentum and the conservation of angular momentum. And there's a in-class demo. I can't do it here. I don't have the stuff, but I will definitely be posting an optional video of this particular in-class demo of the conservation of angular momentum. I literally left my physics class when I was like a sophomore and immediately went and changed my major after I saw this one demo. So please, if you have time, check out the optional video that I'll post along with this lecture video. It's really freaky stuff, and it was the first time where I remember it was the first time I ever remember seeing physics and being like, this is weird. Um, but the whole idea behind it, go ahead and give you the background, is the idea of conservation of angular momentum. So I can at least give you the basics here, and then you can go look at some cool in-class demos later. Um, like we talked about, things rotate, will continue rotating until something stops them. So a rotating object has some sort of inertial rotational energy, or this inertia of rotation, just like linear moving objects have this inertia of motion. With the whole inertia of motion idea, we talked about linear momentum. That's how we sort of quantified it and put a number to it, which is mass times velocity. So the same thing, the inertia of rotation, we just stick the word angular in front of momentum. So the inertia of rotation is just angular momentum. Uh, like you probably remember, linear momentum is represented by P equals mv, just mass times velocity. Angular momentum is very similar. So it turns out it's represented by the rotational inertia. So this is sort of like a mass, kind of, except we get these I values. And depending on which type of object you're talking about, you have to take these values and plug them in for I. So we have the rotational inertia, then we have the rotational velocity. And if we relate it to our linear case, that's like V, except we're talking about an angle being swept out now instead of a rate traveled across a straight distance. So that's going to be our omega, which is just how fast your angle is changing over some sort of time. I is, as you probably remember, the moment of inertia, and omega is the angular velocity. If an object is small compared to its distance to the axis of rotation, then we can actually rewrite the angular momentum, and we can express it actually as linear momentum, just multiplied by a radial distance. So here, let's check it out. If we have this small object, well, that looks pretty small. So that's a small object compared to this distance. Yeah, I'd say it's like what, 10% that distance? So that requirement checks out. Okay. Well, we know this thing has a mass, and we know it has a tangential velocity, right? So this is our tangential velocity. Well, all we need to do is we can actually multiply the mass times the tangential velocity. And that's really just our regular old momentum. And then we just multiply our regular old momentum by the distance from the axis of rotation. And we can actually write angular momentum in terms of linear momentum, p, because that's just mass times velocity. And we have that in our equation here. So something to keep in mind with this whole idea of angular momentum is a particle or a projectile that's launched as a projectile and spins like a bullet or a football If you want to throw that perfect spiral, spinning object, even if it is a projectile and it has linear motion, um, the spinning will actually keep it from starting to tumble. And that's a little bit of what you're going to see in this super cool in-class demo that I keep talking about. So just as an external net force is required to change the linear momentum of an object, force, linear momentum, just like that, we need a external net torque to change the angular momentum of an object. So we're making this association some more here. We can state a rotational version of Newton's first law, actually, and essentially say an object or system of objects will maintain its angular momentum unless acted on by an external net torque. So that's literally the whole: an object in motion stays in motion, an object at rest stays at rest. So we just replace rest with the word rotation, same thing. So this means that the angular momentum of the entire solar system, all these things in our solar system that's rotating, if we look at a big picture, draw a big system around all that, that angular momentum will stay the same forever, right? Because it's conserved. Which leads us to the next slide. Just like the regular old conservation of momentum and the conservation of energy, which we talked about last module and module before that, there's another conservation law, and it's the conservation of angular momentum. So if there's no net external torque acting on a rotating system, we've heard that before, then the angular momentum of the system remains constant. This means that with no external torque, the product of the rotational inertia and the rotational velocity at one time, right? So this is at one time, will be the same as any other time. Let's consider this man standing on this turntable. So he starts a lot of mass far away from the axis of rotation. You can draw that in, right? He's got lever arms for his, he's got some torque going on because he's got big masses, lever arms over here. Okay, so he's got a large amount of inertia, so he's going to turn slowly. You can see that here we've got a big I, a lot of inertia, small speed, so the omega is small. When he pulls his arms inward, his moment of inertia decreases, right? Because inertia depends on R. So your inertia depends on R. I guess we could write it this way as well, instead of using the open face infinity. Well, since the inertia depends on R and he makes R smaller, well, his inertia afterwards is going to decrease, right? You see that here, small I. But since angular momentum is conserved, something must compensate, right? Something's got to change so we can keep the before angular momentum and the after angular momentum the same. Well, therefore, he has to speed up on the turntable, right? So this is Mother Nature trying to make sure the amount of angular momentum he starts with is what he finishes with. So since he's shrinking his inertia, Mother Nature has to increase omega, which means he's going to spin much faster. And you can see this in ice skaters. When they pull their body in, they spin faster, and then when they stretch their arms out, they go slower. Let's look at this example a little bit more. So is it correct to say that the spinning man increases his angular momentum when he pulls his arms inward? And obviously it's no. So in this maneuver, the man's angular speed increases when he pulls his arms in, but angular momentum remains unchanged. It's always conserved. And here's just an example. You can see when this ice skater jumps up into this triple axel, she spins fast, and as soon as she hits, she throws her leg out. And when she kicks her leg out, see how much slower she goes? That's because she, right there when she lands, she instantly increases her moment of inertia, and that slows her down so fast. You can also think about this other example with a gymnast doing a front flip. Um, his rotation is slow when he starts, but notice he pulls his body in, and through here, his rotation speeds up. He gets into full rotation really quick, and then he stretches out again, so he increases his R compared to this little baby R here. He increases his R, and then omega becomes slow again. You can actually see cats do this. They actually use this momentum conservation, angular momentum conservation, to actually flip quickly. I don't know exactly what it is. They do something with their spines, but essentially they tuck and then they can turn really quickly. And you can sort of see that in these first two steps. It is like a tuck and roll, but essentially they have this like conserved momentum, and that's how they figure out and the physics that they use to flip over fast when they're falling. Astronauts actually use something similar in space to reorient their bodies when they're flying around if they need a specific position. They figured out ways that you can move and turn yourself to use this idea of conservation of momentum to make sure you're pointing in the direction that you want to be pointed in. I've got a few links here to some things that we talked about throughout the lectures. But that's going to be it. Yeah, this was short. I just wanted to introduce the idea of conservation momentum. And as long as you remember that the momentum, specifically the angular momentum that you start with, has to be the angular momentum you end with. Keep that in mind. And please, again, go watch those in-class demonstrations. I guarantee you it's going to be worth your time.